Hello and welcome to Homework 4 Overview, or walk through the code, whatever you want to call it. So we think about Homework 3. Homework 3 basically cleaned up the text and kind of, did the text pre-processing. There are millions of different ways to do text pre-processing. Homework 4 really answers the question, hey, what is next? How do we turn words into numbers? Because machines use numbers, okay? And once we turn them into numbers, then we can kind of do things. So that's kind of what this Homework 4 does, is it bridges the pre-processing, Homework 3, and the LLMs or machine learning. So how can you feed a word, a good word, into a neural network? Well, to do that, you need a vector. That's what this homework is for. Okay. How to put the questions on here? Oh, there we go. I did. I just didn't reload the page. So just overview, just 10,000 foot overview real quick. Parts 1 and 2 kind of set up the data set. Part 3, we basically train our own Word2Vec model using Ginsum. I never know how to say that. I'm going to go over a couple of the models we use too here. Number 4, this is where we start querying that model for similar words. And think about how that might be important. Terms change over time, or we want to know, I might say one word and you might say a different word. Well, this is how we can kind of look for those. Now, part 5, because not everything is, I don't know what saying, roses, we want to find failures. If good is one vector, bad should be the opposite vector, but is it? And that's what we kind of look at in part 5. And then, we'll go into parts 6 and 7 here in a bit. The question is, though, which similarities make sense? Which ones surprise you? What document embedding failure? Good and bad. I'm going to show you that one. I think that happens in this data set. Which analogies worked? Which ones didn't work? This is where math and the vectors go to what you think should or should not be related. How do embeddings differ from pre-training? This is the domain question. A model trained on movies knows more about different things than one trained on Twitter data or medical data. We learned last week how to clean text. This week we'll learn how computers really understand words by tuning them into a list of numbers with similar meanings that are kind of similar to each other. So let's get started. Yeah, I'm just going to go to the GitHub folder. There's this. And here's a PDF on kind of how to do it. And remember, the PDF has this nice little pictures. I just did pictures this semester. You see right here. These are close. Worse and bad are very similar words. But now, if I look at this, good and bad, they shouldn't be this similar. So there's a failure right there. Love and hate, they should be on opposite ends of the spectrum, and they're not. They're very, very similar. Here's the questions. Okay, so let's get started. Where is, I'm going to download the notebook. Boom, let me download it. Hold on 1 second, let me get in another program. Okay, well, before we do this, let's explain some of the basic Python libraries. You can Google this. I literally wrote something and then had it make it sound more intelligent, to be honest with you, because I'm horrible at writing this stuff. So NLTK was one of the very first packages, the Natural Language Toolkit. And yeah, it's the oldest and most educational option. It provides fundamental tools like stop word lists, tokenization, and there's standalone tokenizers and stemming. Now, it's great, but the problem is with unstructured text or language, we get these really, really big chunks of data. We get these really big corpuses. So that is why Spacey came out, because it's, I guess, written in C. If, I think it's, I've never verified it, but it's C. It's much faster. And being faster, you can actually use it and more stable. to do the same thing as pretty much as NLTK. I can't make it bold. And it also has some newer features, part-to-speech tagging. That's, hey, this is a noun, this is a verb, etc., etc. It does NER. It says, hey, Sony is a corporation, Ford is a corporation, Tim Cook is a person. We'll cover that here in a bit. Now, Gensum, I think that's how you say it. It is kind of more designed for turning text into vectors, numbers, direction. It's where we train Word2Vec models. There's other ways to do it, but this is just a nice, easy way. Then finally, scikit-learn. So I have I think 2 books of scikit-learn. So scikit-learn uses, or we use it to help evaluate models. We use it to help train models. We can do dimensionality reduction, like PCA and many others. Scikit-learn is a tool that we use very, very commonly in a lot of different applications. Somebody just emailed me about it a couple days ago, so I kind of want to break down what the differences were. Now, these are more the classic up above. These are more the classic ones that we use really before LLMs. And this is kind of one of the newer ones. And then scikit-learn is just more of a machine learning toolkit. If you have questions, let me know, or Google it. Go from there. I'm not going to save this. Okay, well, I'm going to connect to Colab. An A100. I don't want to wait too long. I'm just going to hit run all really quick. So you can see that's why I want to cover that. And we're just using the Stanford movie database. So it loaded 2,500 documents. And actually, I'm going to wait a second. It should train relatively quick because I'm on the A100, but I'm still going to just pause the video here for a second. Okay. This took just over 2 minutes on the A100. But I want to show you something too, because I thought about this. Let me go over here. So here's Safari. And this is just the exact same thing. That's what we did. However, the thing I'm going to do is go change runtime right here. I just selected A100. And you can use a T4, you can use an L4, you can use A100. Probably should make sure that you have a GPU attached to it. And then run all. And instead it should be about the same time. 1 to 2 minutes on here, and I think I was at 2 minutes and some change. Like 2 minutes and 10 seconds. And so what this is doing right here is, this is telling us that it doesn't need the token. So it's basically the corpus equals sentence, or sentence equals corpus. Is each sentence is a list of words, okay, for our vector. This is how big we're going to turn a word into. So Richard equals 100 numbers. Sorry about the power up. Yeah. That's what that's telling us. This tells us how many words to the left and right to go. Yeah, that's right. This tells us that each word has to appear in the document 10 times. Okay. So if we have, I don't know, let's think of a word. Apple, Macintosh, but it's one word and it only appears once because it's a typo or space is missing. It will ignore that word. It never gets vectorized. The machine doesn't know that word exists. I got a piece of mail upstairs where they spell my name. Do they have 2 H's in it? I think they have 2 H's in it. So for example, that will get skipped. That's what this minimum count does. Workers is just how many, I wonder if that would tell me. Workers is just how many CPU, GPU, how many workers it has. Remember Databricks? Workers. Right there, so I do. Skipgram just basically predicts what's around it. Epochs is like how many times it takes and trains over the whole data. 10 is probably sufficient for this. It's not a huge document, but either way. And C just tells it where to start mathematically. So, yeah, let me go back to Colab, or yeah, VS Code. There we go. Okay, so yeah, 2 minutes, 10 seconds. Yeah, same thing here. Okay, so what we're going to do, if I had a medical term, I might look at medical words. If I had a business, I might look, at merger and acquisition. So, these are test words. We want to see how similar they are. So decent. So the closest words to good in this data set are decent for titles or for this data set. Great, fine, excellent, nice. The closest words, closest vectors, I guess they're words because they converted out, is awful, terrible, lousy. Oh, good, interesting. So good and bad are similar. Let's think about that. That's some type of error. It could be just movie titles, but that's something to keep in mind. Movie is most similar to film. I agree. Flick, I guess, so I don't really use that word. Movies, well, that makes sense. And here's why we maybe do some stemming to see how they're similar words. And this. I don't think these are really that close, but probably people are saying this movie is great. This movie sucked. And so movie and this aren't really related. Okay. So, I guess that's fine. We go down here and we notice that good and bad are very, very close. Love and hate are very close. And again, a lot of it has to do with the movie titles. But if this was to move to production, these would have to be fixed. Because the machine wouldn't know really the difference between I love this movie and I hate this movie. They're too similar. Okay, you're a failure. Find at least one case where embedding gives wrong results. Try words you expect to be similar but aren't. Hey, Richard, I'm not a coder. I don't know how to do this. Where is, I don't know if this is going to work or not, but oops, here. Can you help me with this? I noticed, what if it was, I noticed, oh. Yeah. It was a movie in this, but there might be others. Oh, nope, that didn't work. I'm just going to pause it so we don't have to sit here and watch it think. Okay, it said, hey, I found some things. I'm going to go, yes, allow. And it's hard to see, but here's some. example. Star means actor, not celestial object. Character will mean a fictional role, not a personality trait. Shot will mean cinematography, not gunfire. You know, so there we go. And like I said, you can just ask ChatGPT. Let's keep going down to section part 6. Apologies. Now we look at part 6. And it's old, you know, the example, I think your book uses it, king minus man plus woman equals queen. We're starting to get that context. How do we get that? How do we get that? We take one word minus another word and add it to another word, what do we get? You know, when we take bad minus better, and we add good to it, we get awful. And remember that the example I think in your book is we remove man from king and we add, for sure it's woman, then we get queen. So this is what that's doing. It's really interesting to start explaining or playing around with it. So let's remove movie from star and add planet. If it works. Yeah, Earth. These aren't right, but the first one was, and you can play around with it a little bit. You do the classic one, it is man, remove that from king. I don't know if that will work with this data set, and yeah, woman, see the machine already knows it's such a classic example. Well, I got it backwards somehow. Word 2, so I might have to fix it, but it shows you down here what's going on here. Oh yeah, word 1, so it's right here is my logic error. But yeah. And like I said, oh, that's why I created that right down here. Do this. Compare pre-training models. So when we did the pre-training, that's what we had. But our model, the one we trained, the one that took 2 minutes, we can get better results. So the word good normally hits well. Good hits great. Good hits 2. Then ours, good hits decent. Good hits fine. So these are more, I don't want to say movie related, they're more, the vectors are more closer. You know, this is, you know, a demo of word embedding, and it works great in a curated example. But in real life, you know, as we saw up here, it with this, and I think with movie, they're not perfect. But again, it's really good start. Which similarities made the most sense? Well, good and decent makes a lot of sense. I mean, yes, good and great makes a lot of sense. Now, bad and good, that doesn't make any sense at all. So there, you just good and what was it? Great, whatever it was. Oh, yeah, made sense. However, see my typing. However, bad. What was it? It was a good and bad. Surprised me because they. Okay. Let's errors there. And just keep going. Like I said, don't make it harder than it has to be. Which embeddings differ from the pre-trainings? Right here. That's literally this. And try for a different word. Drama. So here we go for the word drama. The pre-trained model associates drama with horror. Weird. Maybe. Reality. See, a lot of these to me, maybe drama and movie I could understand being similar. But no, drama and comedy, that makes more sense to me than horror. Drama and thriller, yeah, I guess that makes sense. Yeah, so see, these are all closer, than the pre-trained model. So there's the answer to the next one. So let me know if you have any questions. Otherwise, feel free to, like I said, to change the text right here. Because this dataset really starts getting neat when you start using applied or domain-specific data. Have a good day.